The forest floor is a ruthless environment. For a small insect navigating the dirt and leaf litter, life is a constant encounter with swarms of aggressive, hungry predators like ants. At under 2 centimeters long, the unassuming Bombardier beetle appears to be an easy target when it is surrounded and outnumbered by an ant swarm. But as the ants close in, the beetle triggers a violent defense. There is an audible pop, a sudden puff of white vapor, and the release of a boiling, noxious liquid. The attackers immediately scatter, writhing from the intense heat, while the tiny beetle walks away entirely unharmed. This is a highly volatile, localized chemical weapon system deployed by a creature that, on the surface, looks completely defenseless. To fuel this attack, the beetle utilizes 2 specific chemical compounds, hydrogen peroxide and hydroquinone. When these 2 chemicals combine, they create an instantaneous reaction that reaches 100 degrees Celsius, the boiling point of water. On a human scale, if you held a container where a pressurized, boiling chemical explosion occurred, the heat and force would be enough to severely burn your hand or melt the vessel itself. Yet this intense physical reaction occurs inside the millimeter-thin internal organs of a tiny insect. This creates a physical paradox. We need to understand how this creature carries, triggers, and survives a boiling internal bomb without cooking itself from the inside out. Looking inside the abdomen, we see that the beetle carries isolated ingredients in 2 large separate upper storage chambers. As long as the hydrogen peroxide and hydroquinone sit on opposite sides of that thick biological wall, they remain completely inert and harmless to the insect. When the beetle is attacked, strong muscles immediately squeeze those upper reservoirs, forcing the 2 distinct liquids down separate tubes toward the rear of the body. The fluids finally pool together into a specialized reaction chamber, which is reinforced with thick, heat-resistant walls. However, mixing the chemicals is only the first step. The beetle operates a staged biological reactor that requires an active trigger to fire. The trigger comes in the form of specialized enzymes, specifically catalase and peroxidase, which the beetle secretes directly into the mixture. These enzymes cause an instant, violent chain reaction, rapidly expanding the liquid into a boiling, toxic gas. In a fraction of a second, an immense amount of internal pressure builds up inside this tiny, tightly confined space. To release that pressure, the beetle uses a flexible rear nozzle as a directional turret, aiming the pressurized payload directly at the attacker. Even with reinforced walls, a sustained 100-degree chemical blast should logically fry the beetle's internal tissues the moment it fires. This survival comes down to the timing of the spray itself. The toxic blast is not a continuous stream of liquid. High-speed cameras reveal that the nozzle contains a tiny mechanical flap that snaps open and closed in rapid succession, breaking the blast into incredibly fast pulsed bursts. By opening and closing at blinding speeds, this valve creates microscopic pauses in the chemical flow, releasing the boiling payload in distinct packets rather than a solid beam. These micropauses allow the biological chamber to bleed off heat in tiny fractions of a second, preventing the temperature from rising high enough to destroy the surrounding tissue. By managing the explosion through this mechanical rhythm, the beetle maintains a precise balance of internal pressure and temperature. Engineers have spent years analyzing the high-speed footage of this specific micropulse mechanism. The Bombardier Beetle provides a functional model for a major human engineering challenge, mastering high-pressure fluid dynamics without causing system failure through overheating. This biological pulsing principle is currently inspiring the design of more efficient automotive fuel injectors, which rely on delivering incredibly precise, rapid bursts of liquid. Researchers are also applying the mechanics of this microvalve to next-generation fire suppression systems and highly accurate medical sprayers. A defense mechanism evolved by an insect is actively shaping the development of advanced industrial hardware. Millions of years of evolutionary refinement have resulted in a flawless chemical reactor housed inside a 2-centimeter body. A moment of wonder. The beetle's anatomy stands as a reminder that highly refined solutions to complex technical problems can be found in the biological systems already functioning all around us.